Let's now take a closer look at the models that generate the meteorological data we often rely on for energy analysis. These are not measurement instruments, but mathematical simulation of the climate system, built from fundamental physical laws and decades of observation. At a larger scale, we find global climate models. These are comprehensive models that simulate interactions between the atmosphere, oceans, land surfaces, and the cryosphere. They are used for long-term climate projections spanning decades or even centuries and play a central role in the Intergovernmental Panel on Climate Change reports. Global climate models typically operate at grid resolutions of 100 to 250 kilometers, which is sufficient for analyzing large-scale phenomena like jet stream or oceanic heat transport. However, they are not able to resolve regional effects such as orographic rainfall, coastal breezes, or local-scale convection. To address this, climate scientists use regional climate models. These models are not standalone, they are nested within global climate models, meaning they inherit large-scale boundary conditions but solve climate dynamics at a higher spatial resolution, typically from 10 to 25 kilometers. Regional climate models are ideal for capturing mid-scale features like wind corridors, humidity gradients, or continental interior heat waves. However, even their resolution can be insufficient for the spatial granularity required in many energy applications. Think, for instance, of modeling winter heating demand in the dense urban area. Here, subtle variation in shading, albedo, and building density can produce significant differences in local temperature. Likewise, wind speeds can vary dramatically over short distances due to terrain effects, especially in mountainous or coastal environments. This is where dynamical downscaling becomes essential. Unlike statistical techniques that adjust data based on empirical relationships, dynamical downscaling involves solving the full physical equation of the atmosphere at fine spatial and temporal resolution. The most widely used tool for dynamical downscaling is the Weather Research and Forecasting model. Originally developed for weather prediction, it has evolved into a community-supported model capable of both short-term simulations and long-term climate applications. The Weather Research and Forecasting model allows users to simulate weather and climate over a custom-defined domain using nested grids that can reach resolutions as fine as 1 kilometer. Within each grid cell, the model computes wind vectors, air temperature, humidity, cloud formation, precipitation, solar radiation, and more, based on physics, not assumptions. In energy modeling, the Weather Research and Forecasting has been used extensively for wind resource assessments in complex terrain, urban climate simulations, including heat island mitigation, solar radiation modeling on sloped or obstructed surfaces, projection of climate extremes such as heat waves or cold snaps. The real strength of the Weather Research and Forecasting models lies in the internal consistencies of its outputs. Unlike interpolated datasets or statistical downscaling, it generates meteorological fields that obey conservation laws and reflect the actual land surface interactions and energy exchanges happening within the domain. That said, it is not a lightweight tool. Running a high-resolution simulation over several months or years requires significant computational resources and careful model setup. Factors such as physics schemes, nested ratios, land cover inputs, and initial conditions must be chosen with attention to scientific and technical rigor. For example, a single ER simulation at 1 km resolution over a countryside domain may require thousands of CPU hours. Yet the insights it provides, such as identifying optimal wind corridors or mapping solar potential with shading, are often unmatched by any other method. At this point, it is useful to compare dynamical downscaling with statistical approaches in terms of accuracy, interpretability, data needs, and computational feasibility.